A smartphone is designed to reach a tower a few kilometers away. In direct-to-device, we ask that same phone to reach a satellite 500 kilometers up, moving at 7.5 kilometers per second. Nothing about that is a small adjustment. In this lecture, we look at why terrestrial cellular protocols break in orbit and at the engineering choices used to repair them. Start with the physical gap. A terrestrial base station sits still, a few kilometers from the user. Propagation delay is measured in microseconds, and the cell boundary never moves. A low Earth orbit satellite sits 550 to 1200 kilometers up, sweeping across the sky at orbital velocity. 3 consequences follow immediately. Delays hundreds of times larger, Doppler shifts orders of magnitude bigger, and cells that move while the user stands perfectly still. Each one reaches into several layers of the 5G protocol stack. Take delay first. Round trip is roughly 25 milliseconds in low Earth orbit, 150 in medium orbit, and 540 in geostationary orbit. For messaging, that is tolerable. For the protocol stack, it is not. Cellular signaling assumes acknowledgements, and scheduling decisions land inside tightly bounded windows. Push delay up by 2 orders of magnitude, and those assumptions collapse. Hybrid automatic repeat request expects an acknowledgement within a few milliseconds. Under geostationary conditions, it may not arrive for several hundred. The second casualty is uplink alignment. Many users transmit to the same base station at once, so the network measures each user's delay and tells the handset to transmit slightly early. That is, timing advance. On the ground, the corrections are small because everyone is within a few kilometers. Over a satellite link, the distance can exceed 1,000 kilometers, and it changes continuously through every pass. Without compensation, uplink bursts arrive outside their reception window. Synchronization fails, and the link can drop entirely. Look closely at HARQ, because it shows the cost clearly. On the ground, the loop takes a few milliseconds. Transmit, decode, acknowledge, retransmit if needed. Over a satellite link, every cycle stretches to tens or hundreds of milliseconds. Throughput falls, spectral efficiency falls, and radio resources sit idle, waiting for feedback that is still in flight. The fixes are architectural. Run many more HARQ processes in parallel, retune the retransmission timers, lean less on HARQ feedback, or push reliability up to the radio link control layer. Now the frequency domain. A satellite closes on you and then recedes at 7.5 kilometers per second, so the carrier frequency shifts continuously. Doppler shift equals radial velocity over the speed of light, multiplied by carrier frequency. At 2 GHz, that gives a maximum shift on the order of 50 kHz, far beyond anything a terrestrial receiver expects. And it is not a fixed offset. It sweeps through the entire pass. Uncompensated, it prevents synchronization, corrupts channel estimation, and wrecks initial access. Then mobility inverts. On the ground, the network is fixed and the user moves. In orbit, the user can stand perfectly still, while the serving cell races across the ground, and the serving satellite changes every few minutes. Left alone, that produces constant cell reselection and a flood of signaling. 3 fixes recur. Tracking areas are pinned to the Earth's surface, so the network looks stationary to the handset. Paging becomes satellite-aware, deferred until visibility returns. And beam handovers are driven by orbital geometry rather than user movement. Everyone faces the same physics. What differs is the engineering response, and the industry has split 3 ways. The standards route extends 3 GPP non-terrestrial network procedures with satellite-specific timing, mobility, and synchronization. The adapted terrestrial route runs conventional cellular technology from space, keeping handset compatibility while absorbing satellite functions into the network. The satellite-centric route pushes complexity into the spacecraft itself. Onboard processing, very large phased arrays, proprietary radio techniques. To close, D2D is an engineering problem, not a new radio technology. The constraints come from physics: delay, Doppler, moving cells, intermittent coverage, and a weak handset transmitter. HARQ, timing advance, random access, paging, and mobility management must be redesigned rather than reused. Providers differ in approach, but not in the problems they have to solve. Next, we open the link budget itself.